So, as we just left off, let's take a look at the important special case of amplification of pulses. What makes it a little bit different is that when we amplify a pulse, we obviously are no longer in a steady state, right? We're not putting a constant illumination on our amplifier, we're putting a burst of some sort. We'll simplify things as much as possible because the pulse amplification gets complicated, but it's something that really needs to be understood because it's so important today. People use optical amplifiers all the time in digital fiber optic communication systems where you're doing exactly that. You're amplifying weak pulses to make them strong pulses. So if we, just a couple things. This is what we've been considering so far. This is what's known as a CW signal. You know that terminology, a continuous wave signal, where the input looks like this. It's just a constant amplitude light in steady state at a single frequency. Okay, close to that, and we'll actually look at this in greater detail when we look at the semiconductor diode lasers. But close to that is a narrow band modulated signal where you take a slowly varying sine wave and you modulate the light with that. There's some analysis involved, and we'll do that analysis a bit later. But this is essentially the same as this. Okay. What I want to look at now is this case. Okay, these are optical pulses, and again, these are bursts that are important because this is like a 1 0 1 1 0 1, that kind of thing, right? This is one possibility this is what an optical modulator would do to the light to put a high rate data rate bit stream on an optical signal, and there are modulators to do that. We'll actually look at some of them this semester. We'll look at more of them if you take photonics. Okay, what makes this different is here's our ground state, level 1, level 2. We have an initial inversion density, whatever it is, up here. But notice as the pulse comes in, what's it going to do? It's going to burn down the inversion density. The stimulated emission, this energy, will stimulate emission from these atoms, bringing them down to this level, depleting the depleting state 2 up here, but doing it as a function of distance through the crystal, right? So it's burning down in space as well as in time. So it's a little bit more complicated, and we'll have to see how we set that up. So again, remember what we have. We have our input pulse envelope. Here's the envelope. I'm not showing the sine wave with it, right? It's really one of these, okay, and this is the envelope of that pulse. Okay, we have our expression I is C over N times the energy of that pulse. We go through our usual slab of atoms where we're pumping up to pumping up to level 2 and pumping up to level 1. And an important assumption here, we're assuming that this is a pulse, and pulses have a bandwidth, but the bandwidth of the pulse is still much, 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 much less than the atomic transition, which is no big deal of an assumption if you think about it. If you have an optical telecommunication system, the operating wavelength is about 1550 nanometers. That corresponds to about 200 terahertz, just under 200 terahertz. So 200 terahertz is a high frequency, right? So if you have a pulse that has a bandwidth of 10 gigahertz, 50 gigahertz, something like that, 50 gigahertz is much, much, much less than 200 terahertz. So we still could assume that we have single frequency operation, even though we don't. What I'm going to try to do is this problem could get a little complicated and again require numerical solutions, and that I want to avoid here. I want to be able to give you an analytic solution for all this so you can get a sense as to what happens when an optical amplifier, not more a sense, but be able to design an optical amplifier that amplifies a pulse. So we're, again, important assumption, we're going to assume that the bandwidth of the pulse is much less than that of the laser transition. Again, a broadband pulse, 50 gigahertz, 100 gigahertz, is still much, much less than 200 terahertz. Okay, the only real difference, but it's a significant difference, is that our rate equations that we just derived on that last recording, right, are now going to be a function of space and time, as we commented. So what I'm going to do is I'm going to go back. Let me go back to those rate equations. They were back here somewhere, right? Oh, getting close. Yep, there they are. Okay, there are the rate equations as we derived them. Okay, they were functions of time. You looked at things as a function of time back with these when we did this, right? But now I'm going to realize that they're not just a function of time, they also vary in space. N is a function of z and t. And again, this picture kind of captures why that is. Here's the pulse traveling through the slab of atoms. It's, of course, traveling in time. It's a function of time, but it's burning down in space the inversion density as it goes. Okay, so everything is the same as before, except now it's additionally a function of z as well as a function of t. So all I did here was I took those equations that I just pointed to a moment ago, right, that we derived in the last recording, and I simply rewrote them and put in wherever there was a t, I put in if I suppressed a t, now I'm going to write it, a z comma t. And of course now I got to have a partial derivative. Notice that I'm assuming that the pumping, though, is a function of time. Actually, I'm going to assume a constant pumping rate. It doesn't vary spatially. I'll have something to say about this in just a minute. Okay, so the inversion density now depends on both the inversion density and the intensity depend upon the position in the crystal. Okay, the intensity grows as follows. Let the energy density be U as always. Again, we could write that in terms of the intensity, as we have been doing all along, except now, again, it's a function of Z and T. What is the rate of increase? We'll assume again an amplifier. What is the rate of increase of energy between Z and Z plus delta Z? Well, very simply, it's actually, very intuitive. U is energy per unit volume, so if I multiply by the volume, I get energy. dt of that energy is the rate of energy. I'm assuming it's increasing. And what has two components, right? I'm putting energy into the crystal, into the pulse. There's a pulse coming in, and that's delivering energy into the crystal. How much energy is it delivering into the crystal in that distance z and z plus delta z? Well, I have I of z that I put in minus I of z plus delta z. That's an energy flux, so I multiply by the area and I get the energy. So this is the rate at which energy, this is an energy flux per unit time, if you look back again to the last recording, right? So you multiply by the area, you get the energy per unit time, the energy rate. This is the rate at which I'm bringing in energy into my crystal from my pulse, okay, for some arbitrary z and z plus delta z. And what else is going to happen? I'm going to this energy is going to input energy is going to stimulated emission. That's kind of redundant. It's going to cause stimulated emission. I'm going to neglect spontaneous emission. The stimulated emission rate, energy is going to increase due to that, due to the inversion density, the atomic cross section, the input intensity, and I want to undo the volume, so I get energy, so I multiply by the volume. So this is the rate at which energy in this crystal is increasing as a function of time and as a function of Z. Okay, so rewriting it, I just rewrote the thing here. What I did, you'll notice, was I put what I'll do is I'll take this I of z minus I of z plus delta z, I'll divide by delta z and multiply by delta z so that this becomes a derivative, and that's exactly what I did here. I of z minus I of z plus delta z over delta z, of course, is di dz, but of course a partial now. The areas cancel out, and so this is the equation that I'm dealing with. Not so bad, right? The only thing about it, though, is that it's a partial differential equation both in time and in z. Those of you who have had the EL 3008, This is very reminiscent, if you look at it as, if you think about it as a transmission line equation, right? This is a pulse propagating in the z direction in this case, and as you might expect, it's looking like it satisfies some sort of pulse propagation equation. It's a little bit difficult to deal with as it sits, so we do a coordinates substitution. And we do the following coordinate substitute. We're going to put in a moving time frame instead of instead of the time frame that we have t. We're going to make time change with z. We're going to substitute for t. We're going to substitute tau, which is t minus z over c. Okay. So in other words, here's what I have. At time t equals 0, I have my pulse, and it's moving with the group velocity. Let's say. I should really say c over n sub g. I don't know why I left that out, but it's moving with velocity z. Forget about the c. It's moving with the group velocity v. And this point, let's say, is at z0, at time t0. Okay? So suppose I go some time delta t later, t0 to t0 plus delta t. What's going to happen to z? Z is going to go from z0 to, how much bigger is it going to be? Well, it propagates with v sub g times delta t, right? So this is the new value of z. Right? What is t1 here? Here t0, here tau, this tau here, right? At this position z0, I'll call it tau 0, is t0 minus z0 over v sub g. At this new position, z1, what is tau 1? Tau 1 will be t1 minus z1 over v sub g. But what is t1? T1 is t0 plus t. I put that in. What is z1? Z1 is z0 plus vg delta t. Clean things up, equal to tau 0. Okay? So you see, in this coordinate system, this is a stationary time frame. This pulse is stationary in time when I make this substitution for the time variable. Okay, and that's what I'm going to do here. So we do the math. When I take this equation that we just said, this is the substitution we want to make, and we substitute it into this differential equation we have here, whereas our diff one right here that we just derived, it reduces to this. Okay. How did I get that? Well, the details are on the next slide. Also, I give you, and I'll show you how we got it, the solution to this equation. I out is I in times the gain, and the gain here is e to the integral 0 to L. 0 is the input where you start, L is where the amplifier ends, of the inversion density times sigma 2 1 times z. But now the inversion density is a function of position, right? It's no longer independent of that as it was in the past, so I have to worry about integrating its functional dependence as a function of z. Okay, the details of the substitution, as I say, when you take this variable substitution, substitute it in here. I assume you know how to do that. If you have trouble with that, here are the steps that give me the solution. The blue equation is simply this equation here that I arrived at. And how did I solve this equation to get this solution? Well, once again, here are the details. Not very complicated, as you can see. And I got just a couple of steps, and here's the answer that I derived. Okay, so reasonably straightforward. You take a look at that at your spare time. Now, the thing is, this is great. This is great that we have this answer here somewhere, right here. But what is this? What is n star of z comma t? We need to figure that out, and that's going to take a little bit of work. Again, I have the details for you here. It has to come, what we did before, where we did this for the steady state, we set ddt equal to 0 and we solve for n star. We can't quite do that here because we're not in steady state. We have a pulse propagation system. So we have to solve these rate equations for n star, the population inversion density, the reduced inversion density as a function of z and tau now. That gets a little bit complicated, so I'm going to it actually would require a computer solution. So I'm going to make some simplifying assumptions. One is on the pumping rate. Okay, so you could read these words, but imagine this. Imagine this, a very narrow little pulse propagating through the slab of atoms. At the same time, I'm pumping that slab of atoms at rate r. Okay, let's suppose that that pulse is so skinny and travels through the slab of material so fast that in the time that it passes through that slice delta z, no additional carriers have been pumped up to level 2. Okay, so that means the rate R2 is 0. Okay, let me say it again just to make sure. We have a skinny pulse propagating pretty swiftly, somewhere near the speed of light through this material. And I'm pumping up atoms into level 2 at some constant rate. I'm going to assume that the pulse is skinny enough and travels fast enough so that as it fast passes through that little delta Z, I haven't added any additional N2 atoms, or N1 atoms for that matter, in that short amount of time. So the rate, no atoms have been added in that time, the rate of increase is 0, and that allows me to set R equals 0. That's very, very important. I'm also going to assume that all these other relaxations are 0 as well. I'm going to assume that relaxation from level 2 directly down to the ground state is 0. I'm going to assume that this laser material works like an ideal laser material in that N1 empties out instantly, like I've said a couple of times, so that N1 is equal to 0. So N star is simply equal to N2. And I'm also going to ignore spontaneous emission because, again, as we'll start to see as we move along, spontaneous emission is small compared to stimulated emission. So when I set all these things equal to 0, these more complicated rate equations here reduce to a much simpler set of equations, namely here. Okay, and I could directly subtract these things and get the differential equation that I want for dn star dt, and there's all this stuff over here. Okay, we're going to consider two cases. The first is for a rapid decay of the lower level. That's N1, okay? Even for rapid stimulated emission, so even if level 2 is depleted very, very rapidly, where do those atoms go? They go back to N1. But I'm going to assume the lifetime is so fast that N1 is always 0. Okay, so that means this inversion density, N2 minus G2 becomes N1. This is 0, so this is simply N2. That's another simplification, right? But we don't really have to always simplify that. What if it's not an ideal laser material? What if it's a real laser material so that the N1 is not completely empty? Well, then I've got to keep this here, and that's what's known as bottlenecking. Okay, it's just given a name for when the atoms going from level 2 to level 1 are filling up level 1, and they're not depleting as fast as you would like back down to the ground state. And so we'd have to keep the full-blown term here. We could do that with one equation. Take our equation that we got right here, and put a beta here. If the lower level decays instantly, beta is equal to 1. If the lower level doesn't decay instantly, we have this factor to contend with 1 plus G2 over G1. Okay? So now, great. What are we trying to do? We're trying to solve this equation, right? And we even, in a sense, have the solution. We know that we're going to need this, but right here, this is the equation we started with, right? And I gave you the details. Here's the solution to that equation. That was all fine and well, except I don't know what N star is. What is N star? I got to figure that out. So not so bad. We have this equation. That's going to help us immensely. Here, we start with that equation. I just took this equation and I copied it down, and here it is. I'm going to integrate this over Z. Okay, so I integrate over the length of the amplifier, 0 to L of n star of z dz, and I got to keep the time derivative, of course, and that means I integrate the other side too over z. Now, you're going to say, what is that? Well, look at the equation we derived. The id's down here, the I dz, n star sigma 2 1 times I. N star sigma 2 1 times I. Okay, so instead of this, I know this is equal to this. I substitute this. Okay, but good old calculus, the integral undoes the derivative. Right? So the integral from 0 to L of the derivative of I, the I dz, is simply equal to I of L minus I of 0 at time tau. We haven't specified time tau yet. Okay, so we have what this integral is here. This integral dd tau integral is simply equal to this. So good, we've evaluated that. Okay. Now, what is n star? We still need, continuing. We need to say, what is n star? This is what we've gotten so far. So far, so good. Remember the expression for the gain, right? We said here, we have this expression for the gain. Let me copy it down again over here. Here's the expression for the gain. That means if I take the log of both sides, the log of g divided by sigma 2 1 is equal to the integral of the log of the exponent. It just undoes. The log of the exponential function is just the exponent, right? So now I differentiate this. And I know that the integral is this term right here, the integral from, I'm trying to perhaps say too much here. If you just look at my steps, it's easy. The integral of 0 to L, we know the derivative of that, okay? So the derivative of the ln of g would differentiate this, right? Because then if we take this expression, very simple, take this expression, differentiate with respect to tau right here, because when I do this side, when I differentiate with respect to tau, that's this, and this is equal to this, so I put that in here, okay? So it's not so bad. Now, this is what I want to solve, and I do that by, let's say I want to eliminate I in and express everything in terms of I out. Okay, I could just as well go the other way, and I'll show you what happens when we get that, when we do that. I'm going to take this equation then here that we just derived. I'm going to factor out I out. I in over I out is 1 over g. We need to solve this equation now, and that's not so bad to do. D dt of the ln of g is 1 over g times dd tau, I should be saying, right? dd tau of the ln of g is 1 over g dg d tau, okay? This thing is, we could write like this, so I could cancel out the g of tau on both sides here, right? So I get 1 over g minus 1 dg is, all this here is just doing the algebra, and now I integrate both sides over d ln g, and the bottom line expression that I get here is this. I get that, and then one more step here, I get this expression. This is the final, this is simplifying, just doing some algebra, the final bottom line result. One thing very interesting to note, this is the gain as a function of tau. I've gotten z out of the picture, right? This is the gain as a function of tau. That's what I want to know. Notice that when I solve, it doesn't depend on the input, but rather the integral, or the output, I should say. It doesn't depend upon the output, but on the integral of the output over time. In other words, this is the intensity, remember, is an energy rate. So when I integrate an energy rate over time, I get the total energy put into the system, or that has come out, says I out. So the total energy that's come out of the system since whenever I started to whatever time I'm at. The integral of the intensity is known as the fluence. So we'll call that gamma. And similarly, whoops, what happened here? There we go. I don't know why this happens. I touch my mouse in the wrong way and everything goes crazy. This expression here, 1 over that, I'll call the saturation fluence. So here's my answer. Right? After all this, you could follow the math. Yeah, here's the expression for the gain. Okay, in terms of the, you could solve this for G. Okay. In a similar way, remember what I did here? What did I say? I said let's simplify by eliminating IN, and I did this, okay, and got this. Okay, I could just as well said, well, let's eliminate I out and keep it in terms of I in. I could do that too, and I get I'll let you. It's very similar, almost identical in terms of the steps that I do. Some algebra, some integrating, and some simplifying. And here's my bottom line answer. Okay. This might be the more useful one because it's usually the input fluence that you have some knowledge about. You know how much energy you're putting into your system. You may not know how much you're getting out, but we'll take a look at that too. Here's the final bottom line result for the gain as a function of tau in terms of the small signal gain, G0, and the saturation fluence and the input fluence. The total energy, the input fluence again is the total energy you put in to your system. The shape doesn't matter. The shape doesn't matter. It's just how much energy you put in. This whole method of analysis that we just did is known as Franz-Nodvik analysis, by the way. Franz-Nodvik analysis for pulse amplification, I guess in honor of the 2 people who first did it, but there you go. You got enough to do, is it the 3rd homework or the 4th homework problem, I think, on homework set 2 now. We're done with everything you need to know to do homework set 2. Okay? But let me give you the answer for the 4th. You have to get the answer. You have to get it. But let me give you what the answer you should get is. Because it's an eye-opener. If I didn't tell you, I was afraid that maybe you would think you're doing something wrong, saying this can't be right. Well, no, it's optical amplifiers don't work like audio amplifiers or RF amplifiers for that matter. Okay, very simple problem in a certain sense. I'm telling you of an amplifier with a small signal gain of 10 dB. In other words, G0 is 10. And I irradiate that by a simple rectangular pulse. This blue pulse is my input, a rectangular pulse, which is 100 nanoseconds in duration. And in that 100 nanoseconds, it contains 50 millijoules per cc of energy. Okay, so I'm giving you the fluence. Right? The saturation energy of the same system is 100 millijoules per centimeter squared. Okay. What I ask you to do for parts A and B is what I give you the answer for. Part C we haven't done yet, but we'll finish up with part C. Plot the output intensity as a function of time, and then identify the time at which the output intensity is half of its peak value, and what is the maximum energy per cc, that cross-sectional area of the amplifier, that can be extracted from this amplifier. Well, as I said, here's the answer. Look what happened. This drives me crazy. Where did it go? Here's the answer. Here, the blue is my input pulse, my nice simple rectangular pulse as a function of time. Look what happens. This pulse is intense enough so that at the very beginning, it burns down entirely the inversion density. So there's nothing left for other than transparency for the remainder of time. So you see what's happening is whoosh, you're getting a big spiky, you're getting a lot of gain at the input of this thing, but that gain is going to drop, or this is intensity I'm plotting. So you get a big burst of intensity, amplification, right? Here's your input, here's your output. It's like 10 times bigger. Well, it's got a gain of 10. That's a good sign, right? So it's 10 times bigger, but wham, does it fall down fast. Why? Because you're burning down the level N2 so fast. We're assuming that N1 is empty, let's say. You're burning it down so fast that there's nothing left for the remainder of the pulse to be used. So N2 minus N is 0. So you just have transparency after this short amount of time. I drew it on a log scale here so that you could see it a little bit better. It starts out with a small signal gain of, here's the 50 millijoules, a small signal gain of 10, but then quickly falls down to a gain of this is the output equals the input. Right? Transparent. No further gain is achieved. So this is the answer you should get for that homework. Again, I think you'll agree this is very different than what you expect for a lot of amplifiers, like solid state amplifiers, transistor amplifiers, or whatever. They don't really work. They have nonlinearities, but this is not normally what you would expect. So this is what you have to get when you do your homework. If you didn't like this, if you said, oh, wait a minute, this is an amplifier. Amplifiers shouldn't produce distortion. Well, oh boy, where did it go? I touch my mouse and the slides go flying. I don't know why. If anybody knows why that is, some setting is on my computer or something, my mouse setting, let me know. Suppose I want no distortion, so that I want, after an infinite amount of time, tau, I want G to be G0, okay? Well, the only way that's going to happen, this is the gain of tau, set it equal to G0. The only way that's going to happen is if the denominator is 1. So here's the denominator equal to 1. And for this exponential term here, I'll assume it's a small, the only way this is going to happen is small signal, right? We intuitively know that. So that means the energy input is going to be small compared to the saturation intensity. So I'll take the exponential and approximate it with the first two terms of a series. E to the minus x is 1 minus x, and stop right there. And you see what you get when you do that. You get that G0 minus 1 times gamma in over gamma s must be much, much, much less than 1. So again, for no distortion, requires small energy at the input, small signal behavior. Otherwise, you get the kind of result that we saw. Again, I want to draw to your attention that each gain, the gain experienced by each slice of the pulse depends only on the fluence, gamma in, the integral of I of t, not the shape. The shape doesn't matter whether it's a rectangular pulse or a Gaussian pulse or whatever kind of pulse. Picture any kind of crazy pulse you like. There's a lot of pulses that could add up to the same fluence, right? The shape doesn't matter. Just this integral, the total energy that you put into the system. We also see here, due to the nature of this decaying exponential, that the gain experienced decreases with tau. In other words, the front of the pulse gets more gain than does the back of the pulse. Again, that makes sense because the front of the pulse is going to be the first one to start to burn down whatever inversion density is there, leaving very little, like a Pac-Man sort of thing, right? It's eating up the inversion density and not leaving anything for the trailing level of pulse that comes behind it and so forth. So here's, if I amplified a Gaussian pulse, for example, the dotted red curve here is the initial input pulse. For a very small signal, I get very small distortion. My output looks roughly my input. But as the input fluence gets larger and larger, the input fluence times the gain over the saturation fluence gets larger and larger from 1 to 10. It did it again. You see what happens. The front of the pulse is getting more gain than is the back of the pulse. Again, for the reason I said, the sooner it happens to for the guys to get there, the ones to get there first have the inversion density to get their gain from, but they burn down that inversion density and don't leave as much for what comes afterwards. So the trailing edge of the pulse gets less gain. So there's lots of distortion involved in these optical amplifiers. There's always, like with anybody, there's always the temptation to drive them harder. You just squeak out a little bit more. But this is what happens. The only way to avoid that distortion is to stay in the small signal regime. Now, the good news is that you don't often care about the distortion if you're dealing with digital signals, right? You have ones and zeros in forms of pulses. Who cares what the shape of the pulse is so long as you could distinguish a pulse, a 1 from a 0. So if the shape doesn't look the same anymore, who cares? The last part of that homework question, let me just finish up quickly with this, asks you how much energy can be extracted from the amplifier. That's sometimes useful information. What's the most energy I could ever get out of this thing? Well, I have two results that I could draw on. Remember our expression for the gain, where we eliminated I out and got this result, and then our expression for the gain where we eliminated I in and got this result. Okay, I substitute what I'm going to do is solve this for gamma out, and what I want to do is I want to know the maximum energy that can be extracted from the amplifier. So I want to know how big can this possibly be, gamma out. So what I'm going to do is solve for gamma out. This easily, you see, becomes this, and I substitute this expression for the gain in here, and I simplify, and I have the steps for you there. There they are. I do what I said. Take this expression for the gain, substitute in here, do some algebra, and the answer you get is this. Look at this. What is the biggest this could be? The biggest this could be is when this is the biggest it could be, because it's e to something or other, right? So I could neglect the one, and I could neglect that one when this thing gets very, very large. So that's the thing. So where did it go? As this thing gets the gamma out, okay, when this thing gets large, neglect this one, right? And you have gamma times the log of G0 times the exponential. Easy to do. Gamma times the log of G0 times the exponential is simply what, well, when I neglect these ones, and so this is gamma times the log of G0, right? The log of G0 times the exponential is the log of G plus the log of the exponential. And the log of the exponential is just the exponent, right? So we have gamma times G0, gamma times the ln of G0 plus this term, right, which is just gamma in over gamma sub s. The gamma sub s is cancelled. It's harder to say the algebra than to do it. You could do basic logarithm exponential, and this is what you get. So after I let this sit for a long time, so I get the maximum extracted energy after a long time, what's that going to be? It's going to be the energy I put in, right? I'm putting, I'm sorry, the energy I get out minus the energy I put in, okay? And the energy I put in, that's the input fluence that we found is this result right here, okay? And remember we had, again, how many times now, this result for the gain, but after a long time, we take the log of this, right? The log of G0, the log of G of minus infinity. That's when we started, where it had the small signal gain, is just this integral here when I take the log of both sides, okay? After tau equal to infinity, or minus infinity, going back way back when. And we saw that was just sigma 2, 1, or we see the integral of this is going to be the initial inversion density n0, the initial population inversion. So really, it's a very simple result. After you go through all this math, you realize that, suppose beta is equal to 1. Suppose it's the case where the lower level instantly depletes. So there's no level 1, n1 equals 0, right? What is the maximum energy you can get? Well, how many inversions do you have, right? N2, that's how many population inversions you're getting due to stimulated emission, times and that each one gives you a photon, times the energy per photon. How simple. Yeah, you could have almost guessed this. I could have said this to you. You probably would have believed me, right? The maximum energy I could extract is the number of transitions that I have times the energy per transition. Okay. If there's this bottlenecking occurring, that result gets reduced by this factor beta. Okay. This is all words that you could read because these are just, again, reinforcing the fact that if you don't want distortion, you got to stay small signal. I don't need to read this for you. We'll stop here now and turn our attention to what I said is going to be the major thrust of this course, and that is semiconductor diode lasers. The semiconductor diode laser is fundamentally every laser is a quantum device. For sure, we'll see that semiconductor diode lasers depend heavily on an understanding of some quantum mechanics. So what we're going to do here is understand some basic quantum mechanics. The next set of notes I call a primer on quantum mechanics. I would more in humor call it just-in-time quantum mechanics. So okay, that's all I'll say now. We'll pick up next time with some quantum mechanics.